Yeah, we are right here. So, so this is the last part of our feature selection lecture. Honestly, this model selection and model assessment, it's a very generic topic, not just for the feature selection. It's for everything else. Whenever you need to select like bases, select debris, select the RBF size, RBF centers, and whenever you need to select hyperparameters, you need to have the model selection stage and also model assessment stage. So in homework 2, we ask you to implement both and also hopefully to help you to grow this habit of always have a separate testing data and never touch it. And the model selection should not touch the test data at all. So have a very clear separation about what is the generalization area you're trying to use test data to more like a proxy, and cross-validation in the end is a learning stage. Because you are using validation data to pick, to select, actually in the end, to fit the hyperparameter values to the data. Question about this procedure. You can either do train validation test or cross-validation on the train, and for the best selected parameter, retrain the model on the whole train and validation, and then test on the test. Okay. So we talk about underfitting. So in the end, underfitting means model is just too simple to represent all the relevant capacity of my model. It's mostly caused by high bias and low variance. So you might still don't understand what is even bias, what is variance, but just roughly keep that in mind. High bias and low variance. And this reflected in high training error and high test error. And the other extreme of not generalized well model is overfitting, which normally means model is too complex and it feeds almost noise, too much noise in the data. It normally caused by low bias and high variance. We are going to define what do we mean bias and variance in next week. But for now, just memorize it. And it's normally you can use one of the curve we ask you to plot is when you have more and more training samples, you try to plot the training error and test error. Then you see the differences of training error and test error as the training size increases. That's a very good tool to tell you if you are overfitting or underfitting. Okay, now this is more like a simple example. What do we mean underfitting or overfitting for regression or for classification? So for regression, we already emphasized many times before, right? If my regression curve is kind of like a quadratic shape, and I'm using a linear to fit it, and clearly there's a big error no matter how good my curve, this line trying to fit, there's always big errors. This is bias. This means high bias. No matter what curve in this family of, no matter how I feed this line, there's no way I feed the data well. So this is high bias model. And this, it really looks good. That's right. Overfitting really just those type of models. You're trying to get every smaller differences of in the training data. So you can see in this case, it has this wiggly lines fit on my training data. So let's assume if I remove this training data, I remove this data, and my line will be very different, right? Because we might fit in there. So this means high variance model. High variance model means if you do some changes on the training data, the model varies a lot. So this is the high variance model. In the classification case, so we know classification, we try to separate the blue points and red points, right? So this is, if you think about this, is separated to classes, but there are a lot of areas. So no matter what separation boundary lines I'm trying to fit on this training data, there always will be some certain level of errors, actually pretty large. Let's just think about, because I can use this more like the proxy of the line, right? Here, if I do here, and there's a lot of blue areas, if I'm doing like this, it just, no matter what you do, there are big areas there. So which means, it's actually in the end means the model you try to fit quite different from the underlying distribution. And this a little bit better and actually fits better, hopefully through cross-validation, this also reflected to generalize better. And this, of course, it's bad, right? Because just a little bit changes, I mean, assuming this blue point is not selected in the training data, then my separation boundaries will be completely changed. In this case, highly likely to be like this. So just smaller changes on the training data makes this boundary varies a lot. This means high variance model. So how do you remedy the overfitting or underfitting? In the underfitting case, normally you just make your model more complex. So in our case, maybe we ask you to, instead of to fit a linear regression model, we fit a polynomial model. And or you add more features, you just add more features. Or there's another case that actually you train more iterations, maybe just you haven't trained enough. Or the learned parameter is still very far from the true parameter. That's the other case, it's also called underfitting, even under the same model family. Questions about underfitting? Or bias? We have a formal definition later. So in the homework, in homework 2, we have a data generation code. If you think about it, it's pretty weird, right? Why do you have a data generation code and then ask me to fit? So the reason why we have a data generation code is actually to simulate, to tell you, all this machine learning models has assumption. That assumption assume there's a true model in the task. And what you're trying to do is always using data to discover that true model, which is exactly how our homework 2 is designed. You have a true model generated data, and you use the data to try to learn that model. And later we're going to define, and actually in the next week, the definition of bias in the end is the learned model and the true model. The differences among the two is bias. Question? Okay. Yeah, so there's a very important concept, is the true model, which is the reason why we have that data generation code, which exactly is the true model, right? It's generated data. All right. So for the overfitting case, what should you do? You simplify the model. So one of the good strategy to simplify the model is regularization, right? If you remember, L2 is to penalize the large weights, L1 to penalize the small weights. And you can also, from polynomial model, instead of doing large D, you do smaller d. You can also just add more training data. Also can just remove those less relevant features. They are all very effective strategies to conquer the overfitting. All right, question about this? Okay. So now let's move to the next. So I already talked about you actually what is bias, what is variance. Bias is how much the average model over all the training data differ from the true model. So, and it's in the end, it's the error due to assumption, due to your assumption. And it's mostly it's a simplified assumption because if your model is more complex, in most cases you can like highly polynomial, hopefully if you have regularization, it can regularize to fit lower degree true models. And variance is how much the model estimated from different training data differ from each other. That's what I meant. If you have some changes on the training data, how your model varies. And this is the property called model variance. Model bias is how is your model on average differ from the true model. All right, so this I'm trying to show you about variance again. So hopefully this one has a higher variance because it's very easy to tell. If you have this data is not selected into training, the curve will be look like this. And if this data and the curve will slightly shift, and if this, in the linear case, it's just one data got not selected, it's normally we'll just do smaller, as long as you have enough training data, your learning curve will not differ that much. So the more complex the model are, the more sensitive to the training data. So what I want to trying to say is, the model complexity, when the model complexity increases, the model variance naturally increases. All right. So, and this is the curve we ask you to plot. So the test curve, so in the cases, assuming you know a good performance you look for, and so you actually can just have more, if you have that luxury to vary the training data, you vary the training data, you try to plot the training error and test error. So if, no matter like how much you already reached the largest size you have, it still have a pretty large gap. It normally means what? It normally just means my model is just too flexible, it's too complex. It fits so well on the training, but it's highly likely it fits some noise there. That's why it doesn't generalize well on the testing. Question about this curve? All right, so what can you do? We already covered. It's underfitting, so you can also vary the training data by increasing the training size, and hopefully you know the desired performance, or that's your goal performance. If the training error is pretty large, and also training error and test error are quite close to each other, it's highly likely my model is just too simple. It's kind of overfits the data. Or maybe I just have too few features. No matter what model I do, that number of features is not enough. Question about this curve. Previous stage? Yeah.
So why the training error is increased?
Good question. Well, the question is why the training error is increasing as the training size is increasing. This needs a little bit thinking. Why? When I'm having more training data.
It's harder to fit all the data.
Exactly. So because I'm trying to feed a model on more and more data, right? Think about I'm training a line with this level of training data. So I fit a line here. When I'm having more training data, hopefully maybe here, hopefully here, what is my error? My error will actually be more in general, right? It just there are more type of training data in my training samples. Yeah. Still question about this? Or maybe just a little, yeah. When you have more training data, this line doesn't change, right? But the training error will apparently increases until at some stages go to the plateau. And that plateau is actually something called intrinsic error. It's about the noise. We're going to talk about one later cover probability. Yeah, okay. More question about this?
How do you know the desired performance line?
Yeah, that's a very good question. So the question is, how do you even know the desired performance goal? In general, actually, you do not know. But I think for different domains, you should have certain level of judging about what type of performance is what I'm looking for. So for example, if it's a very safety concerned task, no matter how you model, the aim I'm looking for has to be very precise. That's just defined by the task itself, by the domain. You have to just aim for to reach that level. Alright, so I think we covered, you add additional feature, make the model more complex. So, this is lecture 7 we covered, and now we start a whole new section. So today's lecture 8 is relatively light. There are almost no equations because it's just because the intro, it's more about application, because from the survey, some student really likes to understand how do all these mathematical formulations connect to some real world applications. So this whole lecture, it's all about real world applications. Alright, so let's see where we are. So we finished the regression, and now we're in supervised classification. So the next week, I'm going to cover bias and variance trade-off, which is actually very important. It's a major theorem about how you compare the learners, and so which I normally. So a lot of the previous years we don't the courses actually like other courses for machine learning, like in this in UVA, they don't normally cover this, but I really like the topic here. So that's why I'm going to use 2 lectures to cover the definition of bias, definition of variance. How do you derive it from the expected prediction error? So there will be pretty dry next week, just to give you alert. Yeah, I know there are surveys about why do we need this level of mathematics. Like I told you, I think in the end, it's the foundation, right? Without those level of mathematics, it's very hard to understand why they are important. So the derivation will be a little dry next week, but hopefully I can make it accessible, to the majority of you. Yeah. But today is a fun lecture, just to have a little bit detour. It's easier lecture today. So what is classification? The whole classification, again, nutshell. So for whatever we try to learn, we need to fill in this nutshell. So the first is all the classification tasks, their output is categorical. That's just how we defined it. It's the X to Y type of formulation, and here we don't consider the reinforcement learning, which is also a categorical output if you predict actions. And so in the end, you can think about, you can use supervised formulation in the reinforcement learning formulation. If you understand it, you know what is reinforcement formulation, you can use supervised learning as a module there. Yeah. All right, so why is categorical, but there are many variations of whys. So the popular supervised classification, I just list a few here, like binary classification, multi-class classification, hierarchical classification, multi-label classification, structure, output classification. So I'm going to give you example applications in each. So for the binary classification, just most classic sentiment review for the review notes, review from the user reviews from Amazon, from TripAdvisor. So either thumb up or thumb down, good review or bad review. That's the most classic binary classification. Sentiment or polarity, and which is one of your homework. And we already had this, is this a good or a positive or negative? Or it's also very popular in bio or medical domain. I mean, have some kind of next generation sequencing or gene expression data. I want to classify based on that blood sample, is that lung cancer, highly likely to be lung cancer samples or not. So, and then is the multi-class classification, so that actually the sentiment classification, if you think about, it normally goes to like 5, 4, 3, 2, 1, right? So you can simplify that into positive and negative. But in the reviews, actually our user reviewed, it's a 5-class task. So there are also a lot of image tasks doing classification. So what we meant, multi-class classification means each sample belongs to only one class. So for every sample I, it can only go to a class label, maybe for example J. You can't have multiple labels on a sample. So this means multi-class classification. So in this case, you have galaxy data to capture the imaging data. You want to classify into early stage, intermediate stage, or late stage. There are huge amount of data actually like hosted. It's about like millions of galaxy captured imaging data, and it's a classic classification task. And then another is this hierarchical classification, which is your Y. It's not a flattered C1, C2 set anymore. So in the multi-class classification, your output is a set. There's no relationship among the classes. So in the end, it's just C1, C2, until say maybe M. And in the hierarchical classification, instead, there are relationships among the classes. So in this case, you have C1, maybe this is C4. And inside C4, you actually have C4.1, C4.2. So inside technology, so a news can be, sorry, it's a little bit small, so hopefully you know what's Google News. So when you have a web news page, it's automatically being assigned in one of the leaf node here. So it can be about iPhone, can be about like Windows or Minecraft or IBM. Everything assigned in this lower level class also belongs to this higher level, which is the parent node of them. So if you think about it, the class labels has a kind of tree structure, a hierarchical tree structure. And you can think about more like C1, C2, and then C4. Inside C4, there's C4.1, C4.2. So this is when I'm having an xi, I'm trying to assign my samples into this tree or an ensemble of trees. And if you think about it, there should be a lot of consideration of the relationship among labels when you design the learner. And the most classic hierarchical classification task is text categorization. The generic, most simple text categorization is treating the Y as flattened set. It's a flattened set. And it's really just, it's a very standard supervised task. But it has like enormous possible applications. It's used for news article classification, metadata annotation, automatic email spam email detection. If you think about it, it's more like binary classification task, but it can also detect the spam emails, and also if it's not spam, it can be categorized into maybe about your schedules, about your friend, all this, whatever category you want to have, or the web page classification, or maybe is this a school page about a university page, and then under the school, it can be have a department page. Under the department, is that a faculty page? Is that a student page? Or is that a staff logistic page? Or maybe about IT? And all this, you can just do all this automatic classification just based on the text content. Okay, so if you think about what matters in our nutshell, and our nutshell is the task, representation, the scoring function, this type of Y relationship will be very important for you to design what scoring function you use. So this is very important. Just how do you still use Y minus Y hat? That kind of quadratic loss function? Or what type of scoring function in the classification case, in the binary classification, in the multi-class classification, in this type of tree, targeted tree classification? So this is a question, and then keep that in mind. And this is a very important topic in machine learning to figure out the right proper loss function to formulate this type of classification, and how do you score it in the end? Score the truth versus prediction. Question about this? Yeah, there's no equation here, so, oh no, there's an equation there. Yeah, so actually just give you a rough idea. So there's a classic called hierarchical loss function. So we're going to cover later. For the binary classification, the most classic is and the multi-class called cross-entropy loss. We're going to cover in deep neural networks. The binary cases is something called hinge loss. Maybe I write it here. So there's classic hinge loss for binary classification. Hierarchical loss for the hierarchical type, and also cross-entropy loss for the multi-class. And there are a lot of other type of loss functions. And we're going to hopefully cover each at a time when we start to talk about detailed algorithms. All right, so now because we are talking about text, right? And also one of the future homework is about text. I have to talk about a little bit about feature representation on text. And your homework, the coming homework, is mostly about text, image, and audio. And there's a reason why we picked that. So because first, they are the centric perception task make computer can behave like a human. It can read the images, can understand audios, can read text to understand semantics of natural languages. So that's a predominant task AI should be able to do well. So that's why we pick these three primary data in your future homeworks: text, image, and audio. And image data, relatively, you can think about they're just concatenation of real value numbers. And audio data, it's also similar, they are smooth signals. And one thing very different is the text data. Text data is relatively very different. It's because it's symbolic. There's the other issue is text data has a property of variable length. So when you handle the image data, you can always some kind of fixed size, fixed length and width, and then you can make sure all the examples have the fixed size, the same size. You don't have the variable length issue. And because the smoothness of the image itself, but for text data, you have to have some kind of pre-processing or some kind of model ability to handle the variable length issues. So what I'm going to introduce is the most classic way to handle the variable length. It's called bag-of-word representation. When you have a piece of text like this, I should put it here. When you have a piece of text like this, how do you convert it as a row in our matrix form? Because we can't directly read this and then feed into our numerical classifiers. And we need to represent this into a numerical form that's represented by a matrix form. See, this is a text, right? It might be super long or maybe super short. So the most classic way is called bag-of-words representation, which is, so I have a fixed dictionary about maybe just the common words in the English text. And this is a fixed, which means it's fixed length. You can fix it, right? And assuming I'm only use the top 30,000. This actually gives you a fixed x1 to xp feature variable representation. And then for each articles, you really just need to represent what property my document with that dictionary first word, second word, until the last word. So the majority, you can actually use the counts, right? How many times that word appeared in the document 1, how many times the second word appeared in the document 2, second word in the dictionary. So this is occurrence vector, it's fixed length. It's also numerical. So this is a classic way called bag-of-words representation by can convert variable length symbolic string form of text document into fixed length numerical vector matrix form. And you're going to implement it in one of the homework. Question about this? All right. So, and now let's move on to something called multi-label classification. So in this image, you have mountain. If you want to label the image automatically, you can actually label the image with multiple different words, labels. There's mountain there's castle, there's road, there's also forest. So the task is really just, I have a fixed set of labels, but different from multi-class classification, I can only assign one of the class into my samples. I can assign multiple, in this case castle and mountain. There's a road, there should be a forest if it's possible. But clearly city and car are not in this label. So this is called a multi-label classification task. is different from multi-class classification task, which is I only assign one label from my output set of labels versus multi-class. Only one of the C. All right, so there are a lot of object recognition tasks actually multi-label tasks. The famous ImageNet competition and also MOOC, there are a lot of image object recognition tasks are multi-label tasks because there are multiple objects on each image. And then similar to the text problem, so how do you represent an image? So the modern deep learning, you actually can just feed in the raw image directly and then use layers of representation to learn it. Before the deep learning trend, there's a very important, it's a very neat and easy explainable type of model called bag of zero words. So people just trying to learn these important structures of images, substructures of images, and then convert each image as a histogram of the zero words that you learned maybe from some unlabeled data or huge amount of data. The idea itself are very similar to what we showed before. You have a dictionary. In the text case, dictionary of English common words. In this case, it's a dictionary of zero words. And there's a lot of approach to learn the zero words from unlabeled data. So, and then you can use the same strategy after you represent the images into a bag of representations, and the downstream classification will be very similar. No matter it's text or images or later in the audio classification or music-based genre classification, we also have bag of audio words, very similar ideas in there too. All right, so here it's more, so this is your dictionary of zero words. You represent this image by a histogram or maybe intensity of each zero words, and that's the similar, and this. So just from the histogram distribution, it's very easy to tell this is a face, this is a bike, and this is a violin. That's the before the deep learning, how people handle this task. And it's still a very powerful logic, it's still a very powerful pipeline. Question about this? All right. Yeah, so now we move to something called structured output prediction, which is I have a sentence input. This is an example. My output is this big tree. So my output is not one of the nodes in the tree. So this is different from the hierarchical classification. You try to assign the example into one of the labels in that hierarchical label trees. And this task, this is called a passing task, is trying to give a structured label of the input. So here the screen was a sea of red. So here you have to assign this to the DT and screen to non-freeze, the upper is non-freeze, and then the was is the verb, and C is noun, and there's the build up a non-freeze, and then this is another freeze, and together they build another non-freeze, and non-freeze from the verb and the verb build a verb freeze, and verb freeze and non-freeze together build a sentence. And this is what you need to output. And in the end, if you think about it, this is a very, very complicated task. This is called structured output prediction. It needs to, it's a very extremely complicated classification task. You need to classify each of the word into the part of speech classes. And after the part of speech class, you need to build up what's the relationship of each of the part of speech. It's really the structure of the part of speech to build up the grammatic syntax structure of my current sentence. And it's an extremely difficult task. But it's also classification. You're classifying your input example into this full tree. It's also not a fixed tree because when the example changes, the tree also varies, right? But there are relationship among these labels like the DT and then N. It's normally built up a noun phrase. Those are the intrinsic dependencies among the class labels. Question about this task. This is called part of speech tree parsing task. All right. So now let's move down to audio classification. So I think maybe you use Spotify. I think the majority of Spotify is automatically classified into genre. So how do you? It's a very important important application. So like Spotify or voice recognition, music genre classification, music author attribution, or can you just figure out from small pieces to figure out who is the creator of the piece? So there are a lot of potential applications using this type of audio speech signal based classification. So we can classify we can just kind of categorize the music into your application into genre related, style related, or mood classification, composer identification, recommendation task, or playlist generation, like prediction, hit prediction task, symbolic audio to symbolic transcription task. There are just many potential audio tasks, and mostly you can just use music classification as a module in this application. And when we handle the audio data, there's used to be, so now a lot of large-scale music genre classification uses a deep learning-based framework. So before deep learning, and this is the pipeline people normally use. So normally people will use some classic feature extractor. It's mostly like, I have something in the next slide about what type of feature people normally use to represent audios. And people like always use metadata because they are very important features of represent the properties of the music or the audios. And then you just do similar pipelines. And this feature extraction is also very similar as that type of real words. Here is called code book detection, almost the audio words detection. And so the reason why I'm reviewing all this, even though this are all from before the deep learning, but you can hopefully have some kind of speculation, even though so currently it's deep learning driven, you really just feed in the raw input for those large scale, when you have large scale label data. If you don't, this type of framework still works. And there's a reason why this type of work all have some similar structures. And you can tell they normally trying to learn a fixed dimensional dictionary. The dictionary, it's about English words or Japanese words, Chinese word, or whatever. It represents that dictionary of frequent semantic units. And even in the image case, it's similar. We're trying to extract those frequent image patterns and just name them as real words. And in the audio case, it's the same. Mostly people did is to extract those frequent important patterns and just treat them as a dictionary and then represent the counting samples, whatever sample, as some kind of distributions or occurrence vectors on those dictionaries. And no matter what type of application there is, it all follows some very similar logics behind. And I hope, maybe in the future you're going to be able to try some of those type of packages. They all build up from this logic, the before deep learning regimes. But anyway, so question about this, and then I guess some of you work on audios, you must be much better than me to explain about this. So the audio has complicated features, and there's all this low level, higher level, and culture related features. So if you are interested, and feel free to read it. But in our homework, I think we're going to give you directly high level features. Yeah. So instead of give you directly audio data, we're going to convert it into code book representations. Or we haven't decided, or maybe the middle level. Yeah, let's see. Okay. Yeah, so the most classic actually is something called MC, it wasn't even shown here. Yeah, the peach data, or let's I'm going to explain better when we start homework 6. In homework 6, you're doing audio clustering. In homework 5, you do text classification. In homework 4, you're doing image deep learning based image classification. That's all roughly what we're going to do. In homework 3, there's a big focus is about pre-processing and scalability in algorithm design. And that's all the rest of homeworks. 3, 4, okay. Alright, so we talked about classification, different type of Y, and then let's talk about representation. So how do you represent a classifier? There are many, many different kinds of classifiers, and some of them only model the separation boundaries. Some of them actually uses some local smoothness assumptions without even having assumptions about the boundary at all. Some actually just have a specific probabilistic models about how my data is generated. That's kind of assumptions. And this gives 3 categories of classifiers, and they roughly just fit into discriminative model, generative model, or instance-based model. The discriminative models model the decision boundaries. Generative models actually model the densities of each class. And instance-based classifiers have only assumption relies on, it doesn't rely on any assumption of decision boundaries or class distributions. It only just have minimal assumption like local smoothness assumption. And we're going to cover actually this, the third category first, and then discriminative model, and then generative model. And you're going to implement actually naive Bayes from scratch. And Kenya's neighbor, Kenya's neighbor is in homework 3, and this is homework 5. So homework 3, homework 5, and decision, actually neural nets and deep learning is homework 4. So this is more image data, just to repeat what I covered. This is about text data. So here is more like a scalability, but we don't require, it's more optional. And plus SVM is also covered in homework 3. It's more about pre-processing. So that's the reason why we did not cover pre-processing homework 2. So even though we actually met that difficulties, if we do not scale the data, standardize the data, you're going to have a very hard time running gradient descent on the current homework 2 data. But I'm going to talk about it later. So it's about, there's feature pre-processing standardization extremely important. It's in one of the design in homework 3. And homework 6 is unsupervised model on the audio data. Yeah. Question about the future? Homework 6 doesn't fit here, it's unsupervised model. All right, yeah. So I'm not going to show you a very vintage survey paper, which I still feel I like it. So this is a paper I remember from 2006. It's a benchmark paper comparing at that time using training size 5,000. And it compared 11 binary classifiers on 8 different data sets. And the formulation there's a lot of reason why they designed this. So they fixed the training size and then use all the rest of the test data. Actually, there's part of here also used as the validation, and then to measure the performance. And this is more like, actually, to be honest, this is more in the small data regime. So when your training data is limited, let's see who wins out. So the first whole group, it's all tree-based ideas. And which also maybe if some of you ever compete in Kaggle competition, the recent competition seems always just one winner called XG Boost. It's also a tree-based approach. The first category is a tree-based. It's all tree-based. And they are modeling the decision. It's hard to see its decision boundary. Certain type, it model decision boundary, but through the decision rule type of formulation. And tree, and then the next category is actual SVM. And then is the k-nearest neighbor. And actually, first maybe like neural nets. And then the SVM approach. So this uses 6 different metrics, and then taking the mean and then rank the method. So what I want to also show from this survey is the classification. There are many different type of metrics. It's not like in the regression you have MSE or maybe Pearson correlation. It mostly relies on that too. But in the classification, there are many different kinds of metrics. Metrics is a very important consideration you need to think when you design the formulation and the framework. And also, like, if you look at the small data regime, neural nets actually doesn't perform that well. The neural nets, in the end, it's the popular ancestor of the current deep learning. So the reason why I'm showing this figure is trying to hopefully motivate you to use other type of classifiers when your data, label data, are not that large. Because the asymptotic behavior, in the end, they're actually better classifiers. And they are theoretically more promising and more guaranteed. So for example, SVM is a very good baseline. And in the tree, the random forest is a very strong and very stable baseline too. All right, question about this? I now discourage you to select deep learning based projects because this is trendy. I just want to remind you there are actually a lot of other good classifiers when you don't have enough training data. And also, of course, what do you even mean enough, right? The definition of enough actually varies according to the algorithm you're using. All right. Okay, so now we finished the task representation, and then what is scoring function? What is the optimization? I'm going to cover these 2 components in each of the algorithms because they kind of differ from each other. And today, the last part I want to focus on is about metrics. How do you evaluate classification results? So the most important, actually, this is for binary classification. So let me clarify, there are only two classes. There's only true or false. And the most important, what you should generate of y prediction versus the y is this confusion matrix. So here, this actually means true positive. It's predicted as positive, and its true label is also positive. False positive is it's predicted as positive, but its true label is negative. And false negative means its true label is positive, it got predicted as negative. And of course, true negative means it's true negative, it's predicted as negative, it's also true label is negative. And when you have these four numbers, there are various of metrics you can use. Classic is the accuracy, which is really just the number of correctly predicted samples over the size of the samples. So the number of correctly predicted samples over the size of the test samples. And then there's precision, which how accurate is the positive prediction. So here, which means I care about the precision, how precise is my positive predictions. And recall, there's specificity, F1 scores. They're actually, so here I'm just to, accuracy is number of correctly predicted over the number of all the test samples. If you use that four numbers, it's using this equation. The denominator is true positive plus the true negative over all the four numbers together. Yes, it's true positive from plus false positive plus false true negative plus false negative. The summation is the size of the test data. Okay, yeah. So so you can. There are actually even more. Something called false positive rate, false negative rate, false discovery rate, and feel free to read by yourself. They're just there are a lot there. So what I want to focus on, there's only 7 minutes left, is something quite always happen is in a lot of cases your data is not balanced. And in most cases, it's always there's one class is very rare, there's one class very dominating, which create these unbalanced cases. So when you have unbalanced binary classification, it's extremely important. You need to be aware accuracy is a bad metric. So the reason why it's bad is we can do an example. So I hope I have my notes. So when I'm saying the class imbalance, it normally means what? It normally means the true actual positive versus the actual negative. The actual positive, number of actual positive is a lot smaller than actual negative. So this is a lot of cases, right? Because maybe you want to classify the population into some kind of disease stage versus the other undiseased stage. Of course, I mean, those have certain disease are much fewer number than the regular cases, right? That's just the nature of those tasks. Or you're trying to do intrusion attack detection, like in some kind of network system, and by the nature of those tasks, the intrusion attacks is also very, very few. So the traces you observe from network traffic, it's always just the negative, which means there's nothing happened. And there will be very extremely rare positive cases recorded in the history trees, right? So in those situations, actually, if you have a classifier, it has really high accuracy, and the reason is it's much easier if you use ACC accuracy as your goal to optimize, and highly likely the classifier will just learn a classification to classify everything as negative. Because if you classify everything as negative, the accuracy will be, let's use an example to show, I think I have an example. So I have actual positive, maybe versus the negative, actual negative is 1 versus 99. And then I'm having this confusion table from my classifier. This is the actual positive, this is the actual negative, this is the truth, this is the y truth, and then this is the y hat. This is the predicted positive, this is the predicted negative. I can just predict everything as negative. Okay, who has question about this table? Because my current classifier classify everything as negative when I'm giving 100 examples in my test data. This is my classifier 1. What is the accuracy of this classifier? What's the accuracy? Yeah, it's 99 over 100. This classifier is 99% accurate. You see a lot of those papers or tools claiming we are achieving 99% of accuracy, and you have to really ask, what's the class balance ratio in your data? If it's extremely unbalanced data, this means nothing. All right, so now let's introduce a good metric called balanced accuracy, which is 1/2 of true positive over the predicted positive and true negative over the predicted negative, which means I'm separating the two classes to see their accuracy, their accuracies, and then take a mean. You can also do a multi-class case for this balanced accuracy. And then balanced accuracy is what in this case? So I have 1/2, right? True positive over predicted positive. So what is this? True positive is 0, right? Over predicted positive, what is predicted positive? Oh, I can't even calculate this, right? Because there's nothing predicted as positive. Okay, assuming I have a good strategy to bypass this case, I have an epsilon here, smaller epsilon guaranteed to give me 0. I think I'm correct, right? Yeah, it's correct. And then plus is true negative is 99. True negative is the 99, and then predicted negative is 100, which is 0.40, 9.5. Yeah. So this actually shows balanced ACC. Whenever it's the data, if it's unbalanced, we should actually look for unbalanced accuracy. And I have a few examples actually later to show you. So this is the first class when you have this confusion matrix, and this is the second case when you have this type of confusion matrix. So this predict really nicely, and then 1 and 99. Balanced ACC is 1 and ACC is 1, 2, even though there's only one difference here. Yeah, all right, questions? Okay, so that's all for today. Thank you. Yeah.